learn, build, master.
Welcome all to the another interesting video, that is the refrigeration basics, understanding the vapor compression refrigeration cycle and pH and TS diagram of VCRS cycle. Have you guys ever wondered that how your refrigerator keeps your food so fresh? Or how your air conditioner cools your room on a hot day? Well, it all comes down to one brilliant system, the vapor compression refrigeration cycle. In today's video, I am going to break down this cycle step by step, explain how it works, and connects the dot with the powerful tools, that is pressure-enthalpy diagram and temperature-entropy diagram. By the end of this video, I'm sure that you will know more about refrigeration than most of the peoples, and maybe even impress your friends. Come, let's dive in. Refrigeration is simply the process of removing heat from one place and dumping it elsewhere to make the things colder. Sounds simple, right? But the magic happens because of refrigeration unit, which basically works on vapor compression refrigeration cycle, also shortly known as VCRS cycle. This refrigeration unit, which works on VCRS cycle, performs its function with many components in it. But it has 4 key components. The very first, the compressor. Think of this as the heart of the system. Then the condenser. This component rejects heat to a surrounding. Third, the expansion valve, the roller coaster ride of the system. Actually, there are 2 types in expansion valves. The first is capillary tube, and the second one is an electronic expansion valve. We'll explain in detail in further series of videos. Fourth, the evaporator. Just understand the superhero of cooling. So here is the VCR schematic on your screen, showing its 4 key components. So the very first component is the compressor. It's the heart of the system. Function wise, it compresses the low pressure, low temperature vapor refrigerant into a high pressure, high temperature vapor refrigerant. Apart from that, you should note important point regarding compressor when you're working into the real-time refrigeration applications. There is a big no to a liquid refrigerant entering compressor. The reason, it will affect the compressor parts and eventually it will reduce the compressor life. So how to avoid that? I will explain you in the coming part of the video. The high pressure, high temperature vapor refrigerant enters into the condenser. Function wise, condenser rejects the refrigerant heat to the surrounding. So depending on cooling type, condensers are classified into 2 types. The first one is the forced cool condenser. Here the refrigerant is cooled by the forced air by the means of mechanical fan. The second one is the naturally cooled condenser. Here refrigerant is cooled by a natural air, same like our home refrigerators. It has a naturally air cooled condenser. In condenser, the 3 sub-processes takes place. First one is a de-superheating, second one is a condensation process where actual phase change happens, and third one is the subcooling. In the coming part of the video, we'll plot these 3 sub-processes on the pH chart. You will understand better there. As condenser operates at constant pressure, we get output as a high pressure, low temperature liquid refrigerant. So the liquid refrigerant enters into the expansion valve. As I mentioned, it's a roller coaster of the VCRS system. In the expansion valve, refrigerant has to pass from a smaller cross-sectional area, which causes the throttling of the refrigerant, which dramatically reduces the refrigerant pressure and further reduces the temperature. As an output, we get low pressure and low temperature liquid refrigerant. There are multiple types of expansion valves. For example, a capillary tube, then the electronic expansion valve, so which is actually driven by a stepper motor, then the thermal expansion valve. This liquid refrigerant enters into the evaporator, the hero of cooling. The evaporator is placed in the area which wants to cool down. The liquid refrigerant in evaporator absorbs the heat from surrounding area and cools the area. In turn, refrigerant vaporizes with increase in its temperature and hence output low pressure, low temperature vapor refrigerant, which again goes to the compressor and hence the cycle repeats. This continuous cycle gives us the required refrigerant effect or the cooling effect which you desires. In the shown schematic, the above half part is the high pressure zone. It means the refrigerant flows at a high pressure condition, and the below half part is the low pressure zone. The refrigerant flows at a low pressure condition. Let's understand the same refrigeration cycle on pH and TS diagram. Before starting that, let's see some of the basics of pH and TS diagram. These diagrams are like the map of the refrigerant, which denotes the thermodynamic properties of refrigerant at particular condition, and these diagrams changes with change in refrigerant. So let's start with the pH diagram. X-axis here shows the enthalpy measured in kilojoule per kg. It's nothing but that represents the energy content or the heat energy of the refrigerant. Y-axis here shows the pressure measured in kPa or bar, shown on the logarithmic scale. Then here we have the saturation dome, which has a critical point on top. This saturation dome divides the refrigerant liquid region, vapor region and a two-phase region. Left curve is the saturated liquid line. It means the refrigerant at that point on that curve is fully liquid. And the right curve is the saturated vapor line. It means the refrigerant at any point on this curve is fully saturated vapor. Inside the dome, the refrigerant is the mixture of liquid and vapor. Here actually the vapor quality is denoted by X. Let's say X is equals to 1. That is, the refrigerant is 100% saturated vapor. And X is equals to 0. The refrigerant is 100% saturated liquid. For example, if X is equals to 0.25, how to read that? It actually means that 25% of the mass is the vapor and the 75% of the mass is the liquid. So here left side region is the subcooled region and the right side region is the superheated vapor region, as shown in the graph. When you want to plot the refrigerant properties on these charts, right, there are few important lines you need to know. In pH chart, the line coming on your screen, it is a constant temperature line, and the blue line here is the constant pressure line. So these are two basics line. Apart from that, there are many lines on the pH chart. If you want, we can bring another series of videos where we can explain in detail. Coming to an TS diagram, so here x-axis denotes the entropy measured in kilojoule per kg Kelvin. In a simple words, it represents the randomness in the refrigerant. Here the y-axis denotes the temperature measured in degrees Celsius or Kelvin, indicates the refrigerant temperature at different stages of the cycle. Similar to the pH, here also we have the saturation curve with the critical point on top. It divides the liquid region, vapor region and a two-phase region. Here the left curve is a saturated liquid, right curve is a saturated vapor, and inside the curve is a liquid vapor mixture, same as we discussed in a pH diagram. Now you guys are ready with the basics. We can plot the refrigeration cycle what we discussed on the pH and TS diagram. So here on your screen, with a refrigeration cycle plotted on a pH diagram, followed by same cycle plotted on TS diagram. The process numbering is same on pH and TS diagram here. So the process 1 to 2 is the compression process which takes place in compressor. So ideally this process is constant entropy process. So that's the reason you can see a straight vertical line TS chart. It is actually ideally, but in actual scenario it's not a complete straight line. It has been slightly tilted. The process 2 to 3 takes place in condenser. It is a constant pressure process, that is isobaric. As I explained back in schematics, there are 3 sub-processes that takes place in condenser, in which first is desuperheating. In this, refrigerant from superheated condition brought to saturated vapor condition by heat rejection, followed by condensation, that is from process 2' to 2'. It's a phase change process in which saturated vapor refrigerant transforms to a saturated liquid refrigerant, followed by subcooling, that is from process 2' to 3. This assures the full liquid refrigerant exits the condenser. 3 to 4 shows the expansion of refrigerant. Here the process is constant enthalpy process, also known as isenthalpic process. The process 4 to 1, it shows the process in evaporator, where actually the heat from the surrounding is been absorbed by a refrigerant. In that we have two sub processes. First is evaporation process from 4 to 4 dash, which is constant pressure process, that is isobaric, and 4 dash to 1, it shows the superheating of refrigerant. Again, it is a constant pressure process. So as I explained in the compressor, in order to avoid the liquid entry inside the compressor, this is an important process which is carried out in either in evaporator or in suction line heat exchanger. That is the additional component is used in a refrigeration system on the need basis. So basically the refrigerant is superheated and assured that 100% vapor refrigerant enters into the compressor in order to increase the life of the compressor. So that completes all the processes, and here you can see a detailed schematic of our system on your screen. So this cycle repeats in loop and gives us the continuous cooling effect. So here we complete our basic refrigeration VCRS cycle. If you enjoyed this video and found it helpful, smash that like button, subscribe for more amazing content, and let me know in comments which topic you'd like me to cover next. So until next time, the Engineering Essentials signing off.